Hello students, today we learn about module 5 of the syllabus, which is digital signal processors. Okay, we have understood about the specifications of an analog filter, which are specified through the help of Kp, Ks, omega p, omega s. We also described something called as the cutoff frequency. Cutoff frequency is the value of omega when the value of the gain is 1 by root 2 of the maximum value of k. Or in the dB scale, we say the value is equal to -3 decibel. If the cutoff frequency omega c happens to be 1 radians per second, the filter is said to be a normalized filter. I repeat again, a normalized filter is one whose cutoff frequency equals 1 radian per second. Now, the procedure for design of low pass, high pass, band pass, etc. Cannot be different for different cases because it will lead to too many methods and complexity of understanding the idea. Therefore, a common method has been arrived wherein first we design a prototype and then this prototype is transformed to the desired type of filter, which is either low pass, high pass, band pass, or band stop. Now let us learn the different types of prototypes. The first prototype that we use is called as a Butterworth prototype. The other very common prototype that we go for is said to be what is called as SJBIT. So Butterworth and SJBIT are different types of prototypes. First we understand about Butterworth and then possibly we can talk about SJBIT prototype. Now, a very important characteristic of this Butterworth filter is that it will exhibit a very smooth passband. That means that you will not find ripples in the passband. In fact, you will not find ripples in the stop band also. Now, the advantages of not having ripples, but what is the drawback? What is the penalty you have to pay? In the case of Butterworth, you have a relatively wide transition band. So the width of the transition band for Butterworth will be more if you compare it with the other prototype, which is called as SJBIT. Now let us look at the typical magnitude frequency response of a Butterworth filter and make a few observations from it. We have drawn a few plots. The dotted line here is the ideal response of a low pass filter. The same magnitude response, if it is drawn for different orders, it is shown using the different color lines here. For example, n is equal to 1. For first order, the response may look something like this, whereas for a higher order, that is 10, the response may look like what is shown here. So the tendency is that as the order increases, the behavior may approach that of the ideal filter. But please understand, a behavior of an ideal low pass filter can never be replicated. Now in this plot, we can also observe that number one, all the responses, they start from a value which is 1 and decrease or fall thereafter. The value of gain is equal to 1 by root 2 when the value of frequency equals to omega c, that is the cutoff frequency. In fact, this is the definition of cutoff frequency. Now, the Butterworth filter is characterized by its magnitude response. So the equation which has actually yielded this plot above is shown here. And the equation for magnitude response for Butterworth is something like this. Magnitude of h of j omega is equal to 1 divided by 1 plus omega divided by omega c to the power of 2n whole raised to 1 by 2. This equation has to be understood as well as remembered. Now in this expression, we have the quantity called as omega c, which is the cutoff frequency measured in terms of radians per second. Capital N describes the order of that particular filter. Now, from the graph, from the graph, we had some observations. So let us summarize these observations now. So we have already understood that magnitude of h of j omega is termed as the magnitude frequency response. Now, if we are measuring the magnitude frequency response at omega value, which is equal to 0, you should note that all of them should have a gain which is equal to 1. That is, irrespective of the order, the value of gain at omega is equal to 0 should be equal to 1. The second point is that when the frequency is equal to the cutoff frequency, we should get a gain which is equal to 1 by root 2. Now this is true because we have the DC gain, the gain at frequency omega is equal to 0, which is equal to 1. So 1 multiplied by 1 by root 2 is also 1 by root 2. So this is from the definition of cutoff frequency, we have to have a gain which is equal to 1 by root 2 for this particular filter. And this is applicable for all values of n. Similar lines, if we are expressing not in the linear scale but in the decibel scale, then we have to take 20 log. So 20 log to the base 10 of h of j omega will give you the answer, which is minus 3.01 dB. So please note, the value at omega is equal to omega c in the linear scale should be 1 by root 2, and in the dB scale it should be equal to minus 3.01 dB. This magnitude response approaches the value 0 as the omega value frequency approaches infinity. Point number 4. The magnitude characteristics is said to be maximally flat. It is said to be maximally flat if the nth order derivative of magnitude of h of j omega, when we apply omega value is equal to 0, the answer should be 0. And this is applicable for all values of n, which ranges from 1 till 2n minus 1. The implication of this maximally flat is that we will not have any sort of ripples anywhere in the Butterworth response. Other words, Butterworth response is said to be maximally flat. It is said to be smooth in both passband and stopband. Fifth point, the magnitude of h of j omega is a monotonically decreasing function of frequency. That means that if you take the gain at a pair of frequencies denoted as omega 1, omega 2, we find that the magnitude at the respective points are h of j omega 2, its magnitude, and h of j omega 1, that's the magnitude. Now, the value at h of j omega 2, this magnitude will be less than that of h of j omega 1, provided the frequency omega 2 is more than that of omega 1. In other words, if you take any 2 points on the curve and we identify the frequencies omega 1, omega 2, where omega 2 is greater, the gain at the higher frequency is less than that of the lower frequency. And this is true for any pair of frequencies omega, omega 1, omega 2 on the curve. And since the frequency drops, so the observation is very simple. If the frequency is decreasing, it is continuously decreasing. You can never have a rise and fall. It always falls. And if it is rising, it should be continuously rising. So in this case, since it is falling, we call it as monotonically decreasing function of frequency. Okay, next we derive the expression for the poles. The poles of the Butterworth filter, where do they lie typically? Let us determine the location of the poles in the case of Butterworth filter. We start by considering the expression for the magnitude squared frequency response. Let us assume that the filter is normalized. Therefore, the value of omega c will be equal to 1. Hence, the value of the denominator in the magnitude response, omega by omega c, so when you are substituting the value of omega c as 1, the denominator becomes equal to 1. Also, because you are applying whole square on both sides, the quantity 1 by n will be eliminated. So that square root is cancelled by the square. Hence, the expression for magnitude squared frequency response is denoted as hn of j omega magnitude square equals 1 by 1 plus omega to the power of 2n. Now this could be expressed as hn of j omega multiplied by hn of minus j omega. So we are associating one part with a positive frequency and another part with a negative frequency. Now, to obtain the transfer function from frequency response, we have to replace j omega with s, and omega will be replaced by the value which is s divided by j, and hence the above equation will become something like what is shown here. Hn of s into hn of minus s is equal to 1 by 1 plus s by j whole to the power of 2n. The numerator here conveys the location of the zeros, the denominator conveys the location of the poles. From this we observe, since there are no s terms, we can conclude that there are no finite zeros. But solving the denominator will definitely gives us the location of the poles. Let us do that next. Now the expressions are written in terms of s. S is the Laplace notation. Laplace transforms are used because we are dealing with analog filters which are continuous. For discrete filters or digital filters, we may adopt the Z transform. Now, concentrating on the denominator term is taken and equated to 0. Solving for s gives you a result which is minus 1 to the power of 1 by 2n multiplied by j. Now here we may perform a substitution. The simplification steps are shown here for your convenience. First we move the value 1 to the other side, it becomes minus 1. To eliminate 2n, we take the power 1 by 2n on both sides. So we get s by j, and minus 1 becomes a power 1 by 2n. Solving for s, we can shift the j to the other side and we end up with the equation that we have just shown. Now in the above expressions, we can make a couple of substitutions. The first substitution is for the value minus 1. Minus 1 could be expressed as e power of j pi into 2k plus 1 with a k value which ranges from 0, 1 and so on. J can be substituted as e power of j pi by 2. Therefore, the above expression for s will now change after substituting the value of minus 1 as well as j to the form which is shown here. We observe that sk is equal to e power of j pi into 2k plus 1 divided by 2n multiplied with e power of j pi by 2 after the respective substitutions. And this equation is applicable for k value starting from 0 and goes on up to 2n minus 1. From the above expression, we can observe that the coefficient of E is 1 or the magnitude is 1. Therefore, we can conclude that all the points will lie on a circle of radius 1. The circle of radius 1 is called as unit circle. Hence, the poles of a Butterworth filter will always lie on the unit circle. The angular separation or the location where the poles lie on the unit circle is determined by calculating the angle. The magnitude we already observed as 1. The phase angle differs by taking different values of k. Therefore, if you compute the phase, so since the expression would be in the form of a into e power of a complex number can be expressed as a into e power of j theta or theta k here in this case. The amplitude we already showed to be 1. Theta k will be the quantity which is there beside j. So we have to inspect this equation and find out what is theta. So theta k here will be 2k by 2n multiplied by pi. 2 cancels and you get pi k by n. The second term will be pi into 1, that is pi divided by 2n, and the third term is pi by 2 because we know that exponents, the power, when you multiply, it results in an addition of the respective powers. So we add the value which is equal to pi by 2, and hence we have got the expression for theta k as shown. This equation has to be remembered so that we can compute the location of the poles. Once again, the expression for theta k is equal to pi k by n plus pi by 2n plus pi by 2. This is to be solved for k value between 0 to 2n minus 1. Now, we understand that totally the number of poles we'll have is 2n because the number is from 0 to 2n minus 1. This 2n can be divided into two parts, that is n and n. One n can be attributed to the left half. As you have already noted, the expression was h of minus s into h of s. So let us call this as the left half and let us call it as the right half. So the poles, they are lying on the unit circle uniformly distributed, and we can associate them to be lying on the left half and right half of the complex plane or the S plane. To understand this better, let us take a few scenarios here. First, we consider the value n, which is equal to 2. For order 2, the expression theta k has to be solved for k value from 0 to 3 because totally we'll have 4 poles. Now, when you substitute the value of k is equal to 0, we end up with theta 0, which is equal to 3 pi by 4. When you substitute the value k is equal to 1 in the above expression, it is the sum of pi by 2 plus pi by 4 plus pi by n, and the answer we'll get is 5 pi by 4. So the denominator here is nothing but 2n, and 2n is equal to 4. Similarly, when you substitute the value of k is equal to 2, we get theta 2 is equal to 7 pi by 4 and theta 3 is equal to 9 pi by 4 respectively. Let us believe that the k is equal to 0, k is equal to 1, they belong to the left half of the complex plane, that is the term Hn of s. Similarly, the term corresponding to k is equal to 2 and k is equal to 3 is associated with the right half poles, that comes for Hn of minus 3. The scheme where we are illustrating this can be observed from the diagram. So on the S plane, you can see the unit circle. Sigma corresponds to the real axis. J omega is the imaginary axis. Circle is of radius 1 and all the poles, they lie on the unit circle and they are equidistant. So S0 is the first pole which we have just calculated, and S1 is the second pole, S2 is the third, and S3 is the fourth. We observe that S0 and S1 will lie on the left half of the complex plane and S2 and S3 are on the right half. We always favor the left half poles because the left half region is a stable one, whereas the right half is said to be unstable. So we favor LHPs over RHPs. A similar exercise can be carried out for order 3. N is equal to 3 is the case where the value of n is an odd number. Now when the value of n is equal to 3, the number of poles we'll get in total is 6. K value ranges from 0 to 5. And solving, we get 3 poles on the left half of the complex plane, and we'll get 3 poles on the right half. So the poles are theta 0, theta 1, theta 2, the respective angles, and theta 3, theta 4, and theta 5. So once again, if we need it, we can plot it on the complex plane, and the placement is shown as follows. So S0, S1, S2, they are the left hand poles which are stable, and S3, S4 and S5 are the right hand poles which are unstable, which probably we may not consider. So since we want a stable filter, we are going to consider only the LHPs, and the transfer function for a normalized Butterworth filter is said to be Hn of S equals 1 by pi, where pi stands for the POS notation, product of sum, and LHP is indicated that we are favoring only the left half poles and we are not considering the right hand ones. The expression can be of the general form S minus Sk, where Sk is the pole value in rectangular system, and the expression after you substitute and simplify shall be called as Bn of S, where Bn of S stands for the Butterworth polynomial of order n. Therefore, by using this general format, we can substitute for the value of the poles. In the case of order 2, in the right we have 2, in the left we have 2, and we are favoring the left half. So the poles which we have to consider for n is equal to 2 is S0 and S1. Whereas for order 3, it will be S0, S1, S2 respectively. So that substitution can be shown here in the case of different numbers of n, we can substitute in that general equation and different answers will emerge. Thank you all.